let's say our vector B1, that's going to be the first vector in a basis for R3. As I'm just typing things randomly here, 4, -2, 7. Of course, it's not truly random because I'm not using decimal places. B2 is going to be another somewhat random vector of 0, 1, -5, and B3 be another somewhat random three-dimensional vector, -2, 2, -4. Okay, enter those. Might have been better to start with a matrix right away. Let's create a matrix that has these vectors as its columns. Since I made the vectors somewhat randomly, in all likelihood, this is a basis for R3. In all likelihood, this matrix is invertible. It's got a non-zero determinant. It's non-singular if it's invertible. We could check the determinant. There it is, 18. I did that with the // at the end. That's equivalent to doing it in front with square brackets. In case that hasn't been clear. So it's got a non-zero determinant. It is an invertible matrix. I think I'll just do // here. We can row reduce it, and we should get the identity matrix, though not in matrix form yet. When you put the commands at the end, they're used in order from left to right. When you put the commands at the beginning, it's more like functions. It's like function composition. You go from right to left. I typically typed it like this. But the output is the same either way. Row reduce does the row reduction matrix form, just makes the output look like a matrix instead of just a list. So we got the identity matrix. This is a set of 3 vectors in R3 that will form a basis of R3. It'll be linearly independent because there's a pivot in every column, no free variables for an augmented homogeneous system. And there's a pivot in every row. Every system would be solvable. This matrix, with these B's as the columns, does form a change of coordinates matrix for this basis relative to the standard basis, the E. What does that mean? It means that you can use that matrix to figure out the old coordinates for any vector if you know its new coordinates with respect to this basis. The matrix typically labeled with a P and often with a subscript for the basis that we're talking about, B. That's going to get multiplied by the coordinate vector of X with respect to B. That matrix in Mathematica will take any coordinate vector relative to the basis B and translate it back to the original vector by matrix multiplication. This is the old vector relative to the standard basis. This is the new vector. Now, it seems a little odd to put the new vector. Wouldn't we be more interested in solving for the new vector? This should seem a little odd. But we can. We can use the inverse matrix. Multiply both sides by P inverse. It is an invertible matrix. Multiplied on the left on both sides. Oh, I made my P cursive there. Lots of subscripts. Use the associative property. Write this. Any matrix times its inverse is the identity matrix. In this case, the 3x3 identity matrix. The identity matrix times any vector gives you that vector. So this equation, the equality between this and this, is another formula equivalent to the original formula that will give you the new vector in terms of the old. Take an example. Wrong notebook again. Let's say x is the vector in standard coordinates 5, -3, 2. What would its new coordinates with respect to this new basis be? Take the inverse of p times x. Matrix form will show the output as a matrix, or in this case, it'll be a column vector. Inverse, I should have called this P. Oh, I didn't call it anything. Okay, let's call this matrix P here. Inverse P will compute P inverse. Multiply times the vector x. This code is essentially implementing this formula, P inverse times x, to give me the coordinate vector of x. There it is. It involves fractions. 2 9ths, 14 9ths, -37 18ths. How can I check that this works? Is there a way to check it? Yeah, use the definition of a coordinate vector. What's the definition of a coordinate vector? If you've written x as this linear combination of the b's, if you found C1, C2, and C3 to make this true, by definition, that means the coordinate vector of x relative to that basis is a 3D vector with the c's as the components. That's what coordinate vectors mean. So we can check this. I guess it's good that I entered the original b's. By taking these scalars, 2 9ths, and multiplying them by the corresponding vector in the basis, times b1 plus 14 9ths times b2. I didn't put a star in there, but I think this will work. Plus -37 18ths times b3. b1, b2, b3 are the original basis vectors. They are these columns entered up here. If I do this, what should I get? Not 0. I should get x back. I should get 5 -3 2. 5 -3 2. Yeah, there it is. Okay, put it in matrix form. 5 -3 2. That confirms the answer. Big picture again. These coordinate changes, these change of coordinates matrices, the P, to new coordinates are related to slanted coordinate systems that we want to define using the straight line solutions, like in the example from last time. I call those eigenvectors. In which that new coordinate system, the system will be much easier to solve because it will correspond to a completely decoupled system. That's why. A diagonal matrix. We'll be able to solve it, and then we'll be able to translate that back to the old coordinate system, x and y, to get our final formula. And also compute things like the matrix exponential and powers of matrices for difference equations. It's all tied together, but it takes a while to get your mind around it. Work on it consistently. All right, have a good day.